Welcome back. I hope the video from the professor from the University of Colorado had been clear on how to simulate an LT-SPICE circuit in terms of body plot and um, get those simulated results. Today we're going to be looking at the waveforms functionality related to body plot within what they call the network analyzer. For that, we have hooked up our RC circuit, the same one that we analyzed on the previous video, with specific values. So the ones that I'm using are for the resistor, it's 300 ohms, and for the capacitor, it's 1 nano. So we have our RC circuit, we have our input, which is going to be given by the waveforms automatically using this network analyzer, and the output is going to be taking out from the capacitor. So it's exactly the same circuit that we study on the transfer function. So we're going to go to this network analyzer tab. We're going to open this network, and we have plenty of options. So let me walk you through this problem. First, we need to define what is the span of the frequency sweep. In this case, we're going to go from 1K to, let's say, 10 mega, okay? 10 mega. That means we're getting 37.5 points each decade, right? Our wave gen is going to be creating a voltage with an amplitude of 1 volts. So that's going to be what we're going to have on channel 1. And we're going to be looking at what is happening on the output. Of course, the transfer function to get the transfer function and see the body plot, we are gonna have to do V2 over V1. But in this case, V1 it's always 1 in amplitude, right? So we can forget about channel 1 essentially. We're not gonna be looking at that. Channel 2, it's gonna be the output divided by 1. So essentially we're looking at the transfer function. So once we have that set up, let's go and run our case. So what is the case doing, or what is the kit doing here? It's doing a frequency sweep. So it's providing an input with certain frequency, and it's sweeping that frequency across the range that we defined here. So let's make it more clear, and we're going here from 0 dBs up to, let's say, minus 30. So let's adjust that to make it more clear. And the phase also, let's use up to 90, I think. That should be enough. And we can move this up and down. Right. So based on the theory or the simulation, you have both options to kind of draw this body plot. You know that this corresponds to a low-pass filter, which start with 0 dBs. Transfer function, it's basically in terms of magnitudes multiplying by 1, right? With a phase of 0. But at some point, right, we know that starts to change. Actually, in this case, you can measure the minus 3 dB, right? Minus 3 dB, exactly there, 500 kilohertz. So if you use the let's say the nominal values, 300 ohms for R and 1 nano Farads for the capacitor, you're going to get a cutoff frequency 1 over 2 pi RC equals 530 kilohertz. And you know that there are tolerances. You looked over this on lab 1. The values are not exactly the values. There are 5% tolerances on these components. So we expect some minor difference. But based on the theory, we know that at minus 3 dBs, we're going to have that cutoff frequency, which corresponds to minus 45 degrees or 45 degrees of displacement on phase, which is exactly what I'm showing here with this red line. What other things you can do with this is you can adjust the units related to the body plot. So on the top, of course, we have magnitude. On the bottom, we have phase, magnitude and phase. But you can definitely consider any other value. Sometimes it's useful to use peak values. So instead of looking at 0 dBs, we want to look 1 here. We can use gain, or you can use RMS. For the purpose of our lab, I think all the activities are related to dBs, but in other applications, you may need this flexibility to change. So I encourage you to build your own circuits, look at this network analyzer, and see in real time what is happening in terms of body plots, magnitude and phase. They're always very, very important. Compare this experimental results with your simulated and your hand calculations, and you should be very, very close. I hope this is helpful. I don't think there are many options here that we can play with. Most definitely, we are not going to have a voltage calculation, sorry, a current calculation. So in this case, we cannot add a channel as a math channel, but what we have enough, it should suffice for what you need to do on your lab activities. Thank you for looking at this video. See you next time.